Alrighty, so welcome everyone, and thank you for the opportunity to talk to you. Hopefully you'll get something out in the next hour. So what we're going to cover is 10 things that you may not know about Oracle indexes, but probably should. Now, you may know some of these things, but hopefully there'll be a few you may not know, and hopefully you'll get some benefit out of the things we're going to cover. Now, the presentation really should be called. Why isn't it moving on? As many things I can fit in to 60 minutes to do with Oracle indexes. So I'm hoping I'll get through all 10 topics, but so I'll talk reasonably quickly, but let's kick on. For those of you that don't know me, this is basically my life in one overhead. And I guess there's a couple of key things to note. One is that I've been around Oracle a little while now, and I don't increment these numbers now. Those numbers are big enough. It just gets depressing having to change the slides every year. And the second important thing to know about me is that I do resemble David Bowie quite remarkably. It's just one of those fortunate things in life. This is a photo taken of me when I was a little bit younger by my mum. And I think you agree that there is a very, very strong similarity between me and the great man. Alrighty, I also have a blog which I keep up to date as much as I can, and if you're into automatic indexes, I'm writing a whole stack of stuff to do with automatic indexes and how they work. And as Connor actually mentioned, automatic indexes, they're already evolving. So compared to what they were when they first came out, there's already been a whole bunch of changes associated with them. So you want to find out about that, look in my log. I'm also running a couple of webinars. I run these periodically, haven't actually run them for a while. Unfortunately for Canadians, it probably may not be of interest because it's going to be probably run about in the middle of your night. But just know I've got two webinars in February, one on indexing internals and best practices. I say best practices in quotes because normally a lot of the best practices really aren't best practices. So I spend a whole bunch of time discussing pretty well everything you would ever need to know about how you actually should be indexing your databases and how to make your applications run potentially a hell of a lot faster. And I've got a second webinar later on in February, which focuses on performance tuning and diagnosing performance issues, both from a database point of view and from a developer point of view. And one of the things I do this is I get people to send me AWR reports, and we go through your AWR reports to find out how we can tune your databases effectively. So so those are two upcoming events. Okay, so let's look at 10 things that you may not know about indexing, and hopefully at the end of this hour you'll know them a little bit better. So the first thing, which is I think always crucial, is to have an understanding on how the cost-based optimizer determines the cost of indexes. Because fundamentally in an execution plan, when it comes to accessing data out of a table, Oracle basically has two kind of choices. One, do I go for the full scan? Do I read everything because Oracle thinks that's the more efficient way to go? Or do I potentially use one of my indexes to access the data? So to sort of illustrate the workings of the cost-based optimizer, I'm just going to create a very simple table here. I've got code. Code has got 100 distinct values. I'm inserting 100,000 rows. So if I want a particular code, I'll be after approximately 1% of my data. I also have an ID, which is just populated with the row num. So it's a unique number. So I'm going to create just an everyday index on my code and a unique index on my ID because it happens to be a unique identifier. Now, there are certain statistics which are crucial for the cost-based optimizer. For the table, the two key things are the number of blocks and, to a lesser degree, how many rows there are in the table. So they're the two key statistics. For indexes, there's a number which are important, the B level, which is how many IOs do I have to navigate to get down to the first leaf block that's of interest to me. Leaf blocks, which is the number of leaf blocks, the actual width of my index. Distinct keys, so how many distinct different values do I have inside my index. And probably most important of all is the clustering factor, which is how well ordered is the data in my table in relation to my index. Because the data in the index is always ordered, has to be. It's always in the index column order. But in the table, it could be in any potential order. So the question of the clustering factor is how well ordered is my data? And if I've got a number which is lowish and approaches the number of blocks within my table, then what that suggests is that I have a very good clustering. I've got very good ordering. Because basically what it means is if I were to read the entire table through the use of the index, it would only cost me 385 IOs to get the data out of the table. Because when I go down and read a particular table block, I can actually get a whole bunch of rows that are interest at the same time. I also have a number of distinct keys, the density, which indirectly gets used, and then the minimum and maximum values of each and every column. So this is my second index on the code. And just note with my code, I have a much worse clustering factor. This is nowhere near the number of blocks in the table. And I would call this what I typically an average or a poor clustering factor. And as I'll go through later on, we'll see that almost all clustering factors are in this range, not very good, meaning I have to do a lot more work if I want to read all the data out of this table, because the data is randomized and I have to go and visit different blocks each time I want to get a particular value, because they're not all logically grouped together or physically grouped together. What I'm going to do also, I'm just going to create a second table, which is identical to the first. The only difference here is I'm actually going to order the data here in code order, meaning if I will now create an index on code for this table, I will have a good clustering factor. Oops, gone too far. I have a good clustering factor. Why? Because the data here is physically in code order inside my table, matching exactly the same order as it is inside my index. So I've got two tables, and effectively they're identical except for the clustering factor of the code column. Now, when it comes to the cost-based optimizer, the other consideration are all your system statistics. So system statistics tells the database metrics about the performance of your database in relation to things such as how fast is a typical single block read, which is the reads that you get via an index. How fast typically is a multi-block read. This is a read I typically would do if I did a full table scan. How fast are my CPUs? How many instructions per second can my CPUs do? And also very importantly is how big actually are the multi-block reads. So it's okay to set a DB file multi-block read count or blah, blah, but for a whole bunch of reasons, Oracle may not be able to meet that criteria. So in my database, actually how big is an average multi-block read in my database? So they're basically the settings of my database. So what I'm going to do now, I'm just going to run basically the simplest query you can possibly run, which is select me a bunch of stuff from my table where my unique index equals 42. So in this example, we can see that Oracle, yes, is using the index. And if we look at the cost, we can see that the cost is very, very low, 2. And we can say conclusively that Oracle is picking this index because 2 is cheaper than the equivalent full table scan, and we'll look at that in a tick. So where does this 2 come from? Well, just note that actually we do perform 3 consistent gets to do this. So to actually 3 consistent gets are we need to read the root block of the index, because remember it's got a B level of 1, so that means I've got a root block which takes me down to the first leaf block. I then read the index entry from that leaf block, that's my second read, and then I've got to go down to the table and visit the actual block that contains the rest of the row that the index points to. And that's it. They're my 3 IOs. And Oracle's saying, actually, the cost of the index is 1. Now, I've just described it being 2. I need to read the root block and the leaf block. But because this is a small index, it's got a B level that's 2 or less, Oracle ignores the root block. Oracle just says, don't worry about costing reading the root block. That's almost certainly case. We don't have to worry about it. So we only concerned ourselves with reading the leaf block, and then it jumps up by 1 in order for us to get the data out of the table, 2. That's where the costs come from. And 2 invariably is less than the full table scan. That's why Oracle's deciding to use the index. Now, when I run the query on code equal to 42, noting that this is 1% of my data because basically I've got 100 different values. I've got the same number of rows for each of those values. So Oracle's picking up the fact that this is actually too expensive. Now, it's got the number of rows spot on. So it's not like the stats are wrong. It's not like Oracle's misrepresenting the number of rows it's getting. It knows fully that it's getting 1,000 rows, that it's got that part right. But it's saying, unfortunately, it's just too expensive to use the index. The full table scan is the cheap alternative. So if you ever have this scenario, there's two things you need to note. One is Oracle's picking the full table scan because it thinks it's cheaper. The cost of the index must be more than 129. All right. And two, if you wanted to sort of investigate what's going on, this is where one of the nice usages of hints. I don't like using hints. You want to do it ad nauseum to fix things, but it is a good way of investigating what the hell is going wrong. Why is Oracle not using his index? So when I hint it to say you basically must use any available index that is valid, Oracle's picked, yep, okay, if you force me to use the index, I'll use the index. But note the cost of the index here is 387. And 387 is way more than the full table scan. That's why Oracle is not using the index. So it's important to understand where these numbers come from. And the numbers come from this very well-known, infamous formula, which basically says that the cost of the index is the B level plus the percentage of leaf blocks I need to read, plus the percentage of table blocks I need to read. So that's basically gives me the cost of using the index. Now, right at the start, Oracle's got to pick what's called the selectivity. What is actually the percentage of data that I need to access? In this example, Oracle knows there's 100 distinct values. You only want one of them. That is 1/100th of the data. That's 1% of the data. So you could put that down when expressed as a point figure as 0.01. If I multiply a number by 0.01, that effectively gets me 1%. So if I multiply my number of rows by my 0.01, this is where Oracle gets the 1,000 rows from. And this is where we now are comfortable that Oracle is getting the correct selectivity. So the reason why Oracle's doing what it's doing isn't because it's got the wrong selectivity, it's because it thinks it's too expensive with that selectivity to use an index. If we now plug this percentage into this formula, the cost then becomes, what's the B level? The B level is 1. However, like I said, if the B level is 2 or less, Oracle does not include the root block. So effectively, example, because Oracle says don't worry about the clustering factor, because remember the clustering factor tells me how many IOs would it cost to read the entire index, to read the entire table through the index. But I don't want to read the entire table. I only want to read 1%. So it's only 1% of the clustering factor. But 1% of the clustering factor is 385. 385 plus the 2 gets me 387. And 387 is just too big. It's more expensive than the full table scan. Now, how do we get the cost of the full table scan? Well, very simplistically, basically Oracle says, well, it's the number of table blocks in your table, and we then divide that by the multi-block read. That tells us how many multi-block reads do I actually need to do my full table scan. And if I multiply that out by the time it takes to do an average multi-block read, that gives me the time it takes me to do the full table scan. So basically it's 496 divided by 20, 496 number of table blocks, 20 is my multi-block read count for my database, multiplied by 10, 10 is the average time it takes to do a multi-block read. That gives me 248 milliseconds. Now, cost in the optimizer's point of view is expressed in units of single block read. So this 248 then get divided by 2 to give us 124. So it's basically the cost of doing the I/O is basically 124 units of single block reads. Now the actual cost is 129. So this is where this 4% of CPU comes in. So the cost-based optimizer considers both I/O and CPU, because CPU, we burn too much CPU, that takes time, that makes the thing take longer. So Oracle's telling us here is that the 4% of this cost is associated with CPU. 4% of this gets us approximately 5. So 5 of this is because of CPU, 124 of this is because of the I/O. The total cost is 129, that's the total cost of the full table scan. 129 is less than 300 odd, where it was previously, 387, therefore the full table scan wins. Now I've just got this rubbish on here, I'm going to get rid of this, go, no, it's not going to. Okay, now, whoop, sorry, I'm losing control here. What I'm going to do is I'm going to run the same query now, but on my BCOUG table. All right, so remember it's the same thing. I'm reading 1% of the data, it's 1,000 rows, but it's on my BCOUG table. And we can see two big differences. And there's a few differences. One, it's automatically just using the index. Why? Because the cost is only 6. It's not 387, it's 6. 6 is less than the 129 for the full table scan, so it just automatically uses the index. And importantly, it should use the index because it's only 11 consistent gets. So now we've got a totally different scenario in our hands. For this particular query, Oracle uses the index because it truly is the more efficient way to go. So where do these numbers come from? The same formula. Note 2 is the same. Using the index is identical because they're both identical indexes. The difference is getting the data out of the table. Here it only jumps up by 4. Previously it jumped up by 385. So the key difference here is the rest of it's the same. The key difference, it's only 1% of a much smaller clustering factor. 1% of 387 gets rounded up to 4. 2 plus 4 equals 6. 6 is much less than 129. Oracle uses the index. So we can see how critical the clustering factor is. The fact that we've got a poor clustering factor can mean typically one or two things in most of our applications. One, it could mean Oracle doesn't use the index at all because it's too expensive. Or two, which is the other very common scenario, it does use the index because it happens to be cheaper than the full table scan, but it's using the index really inefficiently. It's having to do heaps of extra IOs because the data is littered all around the place. And we could still get benefits potentially by reclustering the data, even if it's using the index, because we could potentially use the index much, much more efficiently, as we shall see. Now, what I'm going to do is I want to give you another typical reason on why we will get a poor clustering factor. So what I'm going to do, I'm going to create a table on called BOE ASSM. It's just a normal table. I've got a sequence which is ordered, meaning I'm going to get a unique number that just increments up all the time. I'm just going to create a very simple procedure, and all it does, it just inserts into my table a row, and I'm just getting the ID from my sequence. So that's what it's doing. Just inserts 100,000 rows. But critically, I'm going to run this procedure in 3 different sessions simultaneously. So you can just imagine I've got three sessions running. I'll just go bang, 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 run this procedure in these 3 different sessions. I'm going to create an index on the ID, get all my statistics, and the first thing that spits out is the clustering factor for this ID is terrible. It's 217,000. It's nowhere near the number of blocks inside the table. Now this might be a little bit surprising because I'm actually inserting this in ID order. Remember, I'm just getting the data from the sequence. Every time I do an insert, I'm just getting the next number. But the problem is I'm using ASSM, and ASSM assigns each different session to their own distinct block within the table. And what therefore means is that I'm not inserting the data precisely in ID order. They're just a little bit out. One goes into this block, one goes into its neighboring block, and so it's not quite perfectly in order. And the problem is that when we actually calculate the clustering factor, it doesn't, all it does is it looks at each index entry and it says, do I need to visit a different one to the previous index entry? Do I visit a different table block? If I have to visit a different table block to the previous index entry, I increment the clustering factor. So what could very well happen, if you can imagine this scenario, I've got 3 sessions inserted to a table, they could be inserted into just 3 different blocks. But because each insert goes into a different block on average, it means Oracle for 1,000 rows could calculate a clustering factor of 1,000, even though it actually only goes into 3 distinct blocks. That is the Achilles heel of how Oracle calculates, by default, the clustering factor. And the problem with having a poor clustering factor is when I just want to select a relatively few number of rows, 388 rows in this example, out of a 300,000 row table, Oracle goes, nah, too expensive. You're just going to do too much work. All right. So one thing I will say is if you have a poor clustering factor, don't rebuild the index. This is something that used to be very common advice. It's becoming less common because the more I present, the less people believe in this stuff anymore. But rebuilding the index is not the solution here. You get the identical clustering factor. Why? Because if you rebuild an index, you're not touching the index. That stays the same. You're not changing the order of the data in the table. That stays the same. Therefore, the clustering factor stays the same. So that's not the solution. Now, what can be a solution is from 12.1. 12.1 introduced the ability to have a statistic preference of table cache blocks. And what it does is instead of having 1 as the default, meaning if it's not the same as the previous block I've visited, increment the clustering factor, I could say if it's one of the previous X blocks I've visited, don't increment the clustering factor. So for example, if I say table cache blocks equals to 20, if I'm visiting a block and it's one of the blocks I've visited, one of the last 20 blocks I've previously visited, it will not increment the clustering factor. And the logic here is that if I've visited a block relatively recently ago, that block is almost certainly going to be my buffer cache. So therefore, it doesn't make sense for Oracle to think it's going to do another read because it's almost certainly going to be cached. So why do that? And this is what this table cache block does. It changes the default from being 1 to anything up to 255. And I can set this for a table, I can set this for a schema, I can set this for the entire database. So what I'm going to do is I'm going to try and fix my clustering factor. I'm going to set my table cache block to equal 42. Why 42? Because 42 is the most mystical number in the universe. And if you use 42, mystically, it's almost guaranteed to make things better. All right, so that's why I'm picking 42. If you want to be a bit more conservative, you can pick 16. The nice thing about 16 is 16 mimics the free lists that ASSM in turn tries to mimic. Thereby, if you've got ASSM, 16 will address your issues. That's all you need to set it to. Bugger that, I'm setting it to 42. In fact, in my example, I only had to set it to 3 because within 3 of each other, in most cases, I'll be going to be good enough. Having set it to 42 though, just note my clustering factor has gone from 217,000 to be just 909. It's almost the most perfect clustering factor you can get. So now when I run exactly the same query, a couple of things happens. First of all, it now just automatically uses the index. Why? Because the cost is so much cheaper because now it's a percentage of a tiny clustering factor. But most importantly of all, it's now actually doing the right thing because it's only 6 consistent gets. The data really is quite well clustered. It's just the default behavior of calculating the clustering factor wasn't cutting it. So what I've done here is I haven't artificially reduced the clustering factor. I've actually simply created a more accurate clustering factor. and I've now fixed this query, and I potentially can fix thousands of other queries that have a similar issue. Okay, well, what I'm going to do now is I'm going to create another table with date of birth. And the problem here is my date of births are randomized. I've got 20,000 different dates and they're random. They're all over the place. And because when I create my index, the data is not in date of birth order, I have a terrible clustering factor. No worries, I've got a fix. Table cache blocks. And to get 42, I'm going to set this to be the maximum, 255. Meaning, if I visit a block and it was one of the last blocks, it was one of the last 255 blocks that I visited previously, don't increment the clustering factor. If we look at the new clustering factor, we can see it's only gone down a little bit. Why? Because in this example, the data really is littered all over the place. So table cache block isn't the solution here, because it's not that it's calculating this incorrectly, it's actually calculating this pretty well spot on. It's just the data really is randomized all over the place. So this is another nice thing with table cache blocks, is it doesn't artificially deflate the clustering factor. It simply calculates a more accurate one. And in this example, I've got a couple million rows, but even though I only want 3,000 rows or so, too expensive, too big a percentage of my table. I'm having to visit, says Oracle, most of those 2955 are likely to live in different blocks. That's just too expensive. I might as well do a multi-block full table scan. Okay, just one thing to note, if I've convinced you to start using table cache block, is be careful of the following bug, which is still there with the later versions of 19C. I haven't tested this with 20C and beyond. If I rebuild an index, I've now suddenly got the behavior that I had before. Why? Because when you rebuild an index, Oracle recalculates the statistics. It does that every time you do a rebuild these days. It recalculates the stats. Note when it recalculates stats, it does not use table cache blocks. It goes back to the default of 1. So if you ever rebuild an index and you're using table cache blocks, you must remember to recalculate the statistics again for the clustering factor, because it will stuff it up. Okay. So how do I fix that query? How do I fix my date of birth query so that it actually is nice and efficient and performant? Well, this is one of the things we can start looking at with 12.1 and 12.2. 12.1, 12.2 have provided us a couple of tools that helps us with this. So what I'm going to do is I'm going to add what's called the clustering attribute. I'm going to say to my table, I want this data to be ordered based on date of birth, please. I'm saying without materialized zone maps, if that's the default, but if I had an extra data, I might also want to consider creating a zone map as well. Beyond the scope, I'm not going to discuss that. We're just going to focus on clustering attribute. Nice, that came with 12.1. 12.2 introduced the ability to do an online reorg of the table. So this sets the attribute, but nothing's done instantly. It's when I do the reorg that Oracle now goes, well, when I do the reorg, I'm now going to reorder the data in date of birth order. And guess what? Now I get a minute clustering factor, much closer to the number of blocks in the table than the number of rows. And now when I run this query, remember before it did the full table scan, even with setting table cache blocks, now I will use the index. Why? Because it's only 25. Why? I only need a handful of consistent gets now. 25 to get 3,000 rows is really super efficient, because I'm getting most of the rows of interest out of very few blocks that I need to visit. Okay, now what I'm going to do here, I'm going to create another table, code and grade, and they both have 100 distinct values in both. And they both have terrible clustering factors. One, because I'm inserting this in using the mod function. So I'm inserting 1, 2, 3 up to 100, then 1, 2, 3 up to 100. So they're basically sort of all over the place. And this one's also going to have a terrible clustering factor because I'm using a random number between 1 and 100, which is means I get no ordering. So I've now got 2 terrible clusters on 2 columns. Now, if I want to fix one, like I said, code's really important. I run queries using code all the time. clustering attribute isn't just a case of picking the right column, although that might be important, noting you can reorder something, but just be more flexible to realize if I've got a reasonable number of replicated values, I can use clustering attribute effectively for more than one column. Now, a common discussion is how do I pick which indexes I may want to drop because they're not being used anymore? And we used to have the old index monitoring, and that was used to be pretty useless really, because it only told me it got used yes or no, and then there were a whole bunch of caveats regarding that as well. So 12.2 introduced index tracking. So here I'm creating a table. I've got 1 million rows and I've got a couple of indexes. Note the ID one is unique. Now, there's this new memory view, $$ index usage info. And this basically tells us, has Oracle detected the usage of an index? Yes or no? And how many? So every time we run a query, Oracle samples the queries that are being run and sees whether or not there are indexes being used in those queries in their execution plans. Keyword here is it samples. It samples what's being run. Oh, here you're using this index. Let's keep track of that. What this is done in memory, so it's nice and quick and efficient, so there's not too much overhead in the database. Periodically, about every 15 minutes, this data gets written down permanently into the DBA index usage view. So what I'm going to do, I'm going to run these two queries, one on the ID, one on code. I'm going to execute it 10 times. And I note that Oracle says you have used one new index in the time that this has been running. Now, if you look at DBA index usage, what it does is it doesn't say true or false the index is being used. It actually tells me roughly how often it's being used, how often it's being used in plans, how many rows are being returned, and then it has this histogram of usage. So has it been used to return 0 rows or 1 row or between 2 and 10 rows, etc., etc. So you got some idea of the sort of workload that the index does. And then I think importantly, probably most importantly, it also tells me the last time this index was ever used. So it might be, well, a case you had an index that was used in the application at some point of time, but maybe not for the last 6 months because things have changed. So it gives me all this really useful information. So I can see here in this particular example that yes, it's been used 8 times. Note I actually executed this 10 times, so it hasn't picked everything up, all right? Like it just samples. But if something gets executed frequently, most of those would be counted. If something gets executed very, very infrequently, it's possible that it may not be listed. So if something is not listed, it means it's executed really infrequently. It doesn't necessarily mean it's never been executed. Note, by the way, it hasn't picked up the use of the unique index. So there are some smarts by default where Oracle goes, hold on, if this is a primary key and using a equality predicate, I'm not going to worry about monitoring that because it's going to be obvious you're going to need that index because you're doing an equality predicate on a unique index. That's kind of a no-brainer. You're not going to want to drop that. But if I use a unique index in a non-equality predicate, it can get picked up in the sample mode. So now I've got a much better resource of information to make that crucial decision on whether an index gets dropped or not. If it gets used thousands of times and it got used yesterday or just 5 minutes ago, you ain't going to want to drop it. But if something gets executed and only get used a couple of times and it wasn't used maybe for 3 months, maybe it's something you may want to consider to drop. If you ever drop anything, I'm going to mention a couple of things, but one thing I'll mention right now is don't just drop something, make it invisible first, test the waters for that for a while, and then if the optimizer hasn't complained, the world hasn't ended, then you can drop it afterwards. There are some underscore values where you can change some of this behavior. Oracle by default monitors your first 30,000 indexes that it determines are used in your database. Maybe in your particular example, that may not be enough indexes. In most cases, it would be. Like I mentioned, the default is to only sample. Maybe you want to be a bit more precise. If you've got a database that doesn't have huge amounts of usage, you're not going to burn up too much CPU going mental with this. It's something to consider turning this on. Note there are underscore parameters, so you may want to talk to Oracle first. All right. Now, let's say I do want to drop an index. All right. this is something to be wary of. I've got a table, OK computer, and I'm just populate it full of stuff. All right, that's not too important at this stage. And then I've just got a couple of lookup tables. Key day. Oh, sorry, tell a lie. OK computer and key day are both lookup tables. They're just small lookup tables. It's actually my Radiohead table is my bigger table. Now, I've got these 4 columns, code 1, 2, 3, and 4. Now, each of them have 20 distinct values. Therefore, if I was to get a query that says, get me code equal 1 or code equal 2 equal to something, code 3 equal to something, and code 4 equal to something, there could be 20 times 20 times 20 times 20 combinations of data. That's what there could be. And therefore, Oracle will assume selectivity is tiny, because you only want 20 times 20 times 20 times 20th of the data. But in this extreme example, that's not the case. These values are always the same. So I don't have 20 times 20 times 20 times 20. I actually only have 20 distinct values in this particular table, because there is inherent relationship between these columns. So what I'm going to do, I'm just going to create all my foreign keys and all my indexes, but the key index I'm going to create is one on code 1, 2, 3, and 4. Why? Because I know I want to do a query on that, so I want an index to pick those particular rows nice and efficiently. Now, as I mentioned earlier, one of the key statistics for an index is distinct keys. There are 20 distinct keys. That is a vital piece of information for the optimizer, because now it knows there are only 20 different combined values here, not 20 times 20 times 20 times 20. So therefore, the optimizer can use this. So when I run a query and I do a couple of joins with my lookup tables, note I'm getting where code equals 1 and code 2 equals 1, code 3 equals 1, code 4 equals 1, I'm getting 100,000 rows. And the optimizer has got this spot on. Note, it's not using any index. Why? Because that's about 10% of my table, and 10% of my table is just too expensive to use an index. Bugger that, I'm going to do a full table scan. So note, it's got the cost spot on, but it's not using the index within the execution plan. So what do we normally do? We got an index that doesn't look like it's being used, we drop it. Next time I run this query, all hell breaks loose. Now it's not doing all my hash joins. It's now suddenly doing a merge join. It's doing a sort join. It's doing a full table scan and then doing a sort of this table. Why? Because it thinks it's only getting 13 rows. Because without knowing how many distinct keys there are, and it's now gone, that piece of information is gone with the index, it's now back to thinking I'm going to get one of 20 times 20 times 20 times 20th of the table. That's about 13 rows, thinks Oracle. Hell, for 13 rows, sort merge join would definitely be the way to go. So this is now much more expensive. My plan's blowing up because it's lost this vital piece of information. So the critical advice is this: if you decide, yes, I want to drop an index, but it's a concatenated index, a multi-column index, strongly recommend that you create extended stats first. Create stats on code 1, 2, 3, and 4. That means Oracle will create a virtual column to tell me for that combination of data there's actually only 20 distinct keys. That means when I run this query, I'm back to just doing my hash joins again, and I've got the correct cardinality estimates again. Because now I'm replicating those stats that used to be in the index through extended stats. All right. How are we going with time? Oh yeah, kind of slowly getting there. All right, 20 minutes. I could do it. All right. Now, one of the very common things I see around the traps is wanting to have case-insensitive search. So this is a very sort of typical scenario. So I'm going to make a very simple example here. I've got a table and most of the data is Ziggy Stardust. Okay, and I'm concatenating with a row num. All right, so it's lots of distinct values. Most of them are Ziggy Stardust and a number, but then I've got a few David Bowies. But note that the David Bowies are all in different cases. And I've got another column called alias. Same, most of them are normally all Ziggy. Got a few little Bowies in there, but they're all in different cases. Okay, click my statistics. I create an index on my name. And if I say where name equals David Bowie, as we all know, that's a case sensitive search. All right, it will only find uppercase David Bowies. So the good news is it will find me my uppercase David Bowie, and it will use the index to do so because there's only one of them. But the bad news is that's not really what I want. I actually wanted all the David Bowies regardless of the case. So this is where we can use things like our upper functions. I can say, well, let's upper the name, convert everything to uppercase, and then look for uppercase Bowie. So the good news now is that this is effectively a case-insensitive search, but the bad news now is that I have to now do a full table scan, because once I put a column through a function, this is a black box. I've just got no idea what stuff's going to come out of this, so it can't possibly use the normal index. So now I'm forced to create another index on the upper function in order to satisfy this. Now, now I can actually do this without actually having to do the upper. And note with upper as well, I have to change the code if I want to do that. I actually have to put upper in. So if I want to have a technique, I could always use a linguistic index. This is basically an example of linguistic index. So I'm saying here, I want to create an index. I want to do a sort. I want to sort name in a binary case insensitive manner. So Oracle internally converts the name into a binary case insensitive format and stores that inside the index. And now if I say to my session, I want my default NOS sort to be binary case insensitive, and I want to use by default linguistic comparisons versus binary comparisons, now, yeah, I can say name equal to David Bowie, no need to change my code with upper function, and yes, I can get all my David Bowies regardless of what the case is via an index, via my linguistic index. But the problem with this is that if I actually have another column where I don't want to do that, I actually want to actually do a binary search. So here I create a normal binary index. I don't have any of that sort of linguistic rubbish in there. But because my session is set to do linguistic searches and I say alias equal to Bowie, it says, no, I'm going to find all cases of Bowie. Even though I don't want that, I just want the uppercase Bowie in this example. So it's kind of like all or nothing, one or the other. And it becomes really cumbersome having to swap these session parameters around. And in most cases, people just sort of just give up. So it becomes very cumbersome. Not with 12.2. So with 12.2, I can now have a new attribute that I can assign to a table, to a column, which tells me, do I want it to be the default correlation to be binary case insensitive? So that means for this particular table, by default, I want the correlation, the way I do my comparisons, to be binary case insensitive. All right, so treat it as if it's like a linguistic search. However, for the alias, I want to override the default and I want to correlate it in a binary manner. So now I can do both at the same time very simplistically. So I've got the same data as before. Now I just create a normal index. I don't need all that additional syntax for linguistic. Oracle knows I want to treat this in a case insensitive manner. So when I create the index, it's a case insensitive index that gets created. When I do my comparison, it's a case insensitive comparison that gets done, and I can use the associated index. Beautiful. But for alias, I want it to be binary. So when I create its index, it's a binary index. When I do its comparison, it's a binary comparison, and I can do it. And that way I can have the best of both worlds within the same table, within the same schema, within the same database. I've got much more flexibility. I can alter the correlation for a table, but it only impacts the new column. So if I were to change the default, add a new column, it would inherit the new default. And I can set this for a schema, I can set this for a session, so I've got a lot more flexibility in how I handle these case insensitive searches than I could previously. Now, if I had to pick one feature in Oracle, which is the most underused feature in relation to indexing, I would say compression. And I'm not talking advanced compression, I'm talking basic key compression, which you get for free in your database if you're on Enterprise Edition. You don't get this with Standard Edition, but you do with Enterprise Edition. Now, how does this work? So basically, when I create an index by default, this is the indexed value and I store the row ID, index value, row ID. So if I've got a lot of repeated names, values, I'm storing that value again and again and again within a leaf block. That's how it stores things by default. So with basic compression, what Oracle does, it basically deduplicates the index entries within a leaf block. So effectively, Oracle creates what's called a prefix table. So for David Bowie, that's the index entry. For the following row IDs, they're all David Bowies. I don't have to store David Bowie again and again and again. Store it once within the leaf block, and then I can basically reference all the following row IDs to be David Bowies. I've got a new index entry, David Jones. Store it once, the following row IDs all David Jones. And because I'm not storing the same index entry again and again, I don't have to store as much data inside my index. I don't need as anywhere near potentially as many leaf blocks. So what I'm going to do, I'm going to create a table. I'm just going to create a table based on DBA tables and insert it into itself a few times. Why? I just want to create a whole bunch of duplicate data. That's because this only works when you've got duplicate index entries, and most indexes are non-unique indexes. So you probably have a lot of indexes that do have duplicate values. All right. I'm going to create this index to begin with on owner and table name with a %free equal to 0, meaning don't waste any precious space when I create the index for subsequent inserts. Make this index as small as possible straight off. So 285 blocks is the size of my index by default with no compression. Now, if I look at a block dump, basically this is a hex representation of my ASCII values, and all I need you to note is that they're identical again and again and again, because I've got lots of owners and table names that are the same within a same leaf block. So I'm kind of wasting space by just keep storing the same thing again and again and again. I've only got 218 index entries inside this leaf block. So what I'm going to do now, I'm going to compress it. I'm going to rebuild it with compress. And by compress, I will compress all the columns of my index because it's a non-unique index in this example. And we can see that the index is much smaller. And for dramatic impact, I've even reduced the B level of this index. Now note, that's actually quite a rare thing to do. I'm not going to suggest that by using basic compression, you're going to reduce your B levels, but it's possible. If you've got an edge case, I could make this substantially smaller and even reduce the height of my index. And the key reason why is I've got this prefix part of my index block now. So this index entry is only stored once. And it says I have 32 index entries that have this value. They're the first 32. Then I've got this index entry. It's different. It's somewhat different to the previous one, but it's only stored once. And again, it happens to have 32 index entries, the next 32 that belong to it, and so on. So if I look at an actual index entry, which is down here, what I've only stored in the index entry is the row ID. I don't need to store the index value. I only have to store the index row ID, which is the unique part of the index. Therefore, I'm storing far less data. I can now squeeze 676 different entries inside a leaf block. Okay, now compression works where you've got repeated data. So for non-unique index, I can compress as many of those columns as I want. If I've got a unique index, I can't compress the entire index. That doesn't make sense because an entire index entry would be unique. Therefore, there'd be no duplication. There'd be no way I can take advantage of deduping. So with unique index, the default is it will compress as many columns as there are less one. Meaning if I've got a unique index with only one column, I can't compress it using basic compression. It's impossible. All right. So what I'm going to do now, I'm going to create a table, and I'm based on the previous one, but I'm going to add a new column, row num. And row num is effectively unique. So I've now got a unique attribute regarding this table. I'm going to create an index now with owner, ID. Now, I don't want to compress the entire index because the ID is unique. If I said for every combination I want to create a prefix entry, there'll be no benefit in compressing both columns because the ID portion is unique. But the owner portion isn't unique. That's got quite a few duplicates in it. So here I'm saying I only want to compress one column, the first column. So compress one integer means the first column of the index. It doesn't mean one. So the order of the columns of the index now become important. The first column is compressible, and I'm making this index now be 136 in size. So my prefix entry only contains the first column. The prefix, the actual index entries themselves contains the second column, the ID, and the row ID. The second column and the row ID. I'm still getting benefit because I'm not storing this replicated bit of my index multiple times. Now, if I had an index the other way around, ID owner, this index now can't be compressed. Why? Because the leading column doesn't have enough duplicate value. In fact, in this example, it's got no duplicate values. I get no benefit from compressing this if the first column doesn't have the duplicate values. So this is where column order could be critical for a particular efficiency of my index. Note that this index, even though I'm only compressing one ID, is much bigger than it was before. Because now if I look at my leaf block, each prefix of ID only has one associated index entry, every single one. And in fact, I'm actually making things worse, not better. Why? Because the prefix table comes with its own set of overheads. It has lock flags and delete flags, and there's other associated overheads as well. So if I'm not getting any benefit from deduplication, I'm actually making this index bigger, not smaller. If I rebuild this index with no compression, it's actually smaller than it was when I tried to do the compression. And this is the fundamental reason people don't touch this, because now what you're saying, Richard, is if I stuff this up, I could actually make my indexes bigger. Forget it. I'm not going to touch it. So the two reasons why this is not used, one is because it scares people, because you can get things, you have to think about it, and column order is important. And two, it's not the default behavior, and 99.9% of the time, default behavior is the way things go. However, what I want to show you is a very simple technique of how to ensure that you pick the right value. What you do is in your test database, which is your copy of production, and in most environments I work with, you have a QA prod copy of your database. And what you can do on there safely enough is validate the structure of your index. I won't do this in production because this locks the underlying table. But if you've got a copy of your database, knock yourselves out. And what this does, it populates index stats, and two of the very useful columns is how much compression columns you should compress and what percentage of savings are you likely to get. So when I validate the structure of this index, Oracle's saying don't compress two, compress one of the indexes, one of the columns, and you will get about a 23% saving if you were to do this. You just follow that advice. Okay, compress one, bang, bang, bang. Guess what? The number of leaf blocks has gone down roughly by about 23%. Here I've got my index with the ID leading. Validate structure, 0. Do not compress this. No columns are worthy of compression. So this is a fail-safe way of using basic compression to compress it in the most effective way possible. And this is something I strongly recommend people explore, because it's always a good thing if I can substantially reduce the size of my indexes. Okie dokie. Okay. Now, this is a very common scenario. I've got my status column, and most of the data is processed. So most flights have flown, most bank transactions have been completed, etc., etc. Most things have been delivered, all that sort of stuff. But I've got a few statuses of Bowie. Okay, so there's lots and lots of columns that kind of have this kind of criteria. Most stuff's processed, but I've got a few bunch of other statuses. And yes, I can create an index, and yes, I can create a histogram, and let Oracle know that when you're after Bowies, there's relatively few of those. Use the index to get you the Bowies. And when you're after process, there's lots of those. With the histogram, you'd probably say, you know what, it's probably cheaper to do full table scan. But the problem is that you're creating an index where 99.9% of that index stores stuff you don't want in the index. You never use in the index. So this is where techniques such as using decode functions come in. So I want to decode my status, convert any uncommon value and keep it, but any popular value, I want to convert it to a null. And when I convert it to a null, nulls by default are not stored in my index, so now I don't have to store these common values. So now my new index is much, much smaller because it only indexes the index entries that are of interest to me. So now when I use a function-based index on this, brilliant. It uses the index, I get me the data, I'm only storing the data I need to, but the problem is, again, I have to update my application to use the associated decode. And sometimes I don't have access to the application to do that, or it just takes too long to do that. So what if you've got partitioning? You could use the benefits of zero size indexes with partitioning. So what I'm going to do here, I'm going to create a globally partitioned index, and I'm simply got one partition that has all the common values and one partition that has all the uncommon values. Now you can partition this using any partition strategy that you want, but the key thing is you've got one partition that contains all the common ones and one or more that contain all the uncommon ones, and build it as an unusable index so it gets created automatically. Then only rebuild the portion that you want to use. Leave the portion that contains most of the data unusable. And what that means is Oracle never creates a segment on that. You've only got the segment on the bit of the data you want to index. So now, whoops, sorry, gone too far. Now, without ever having to update my application, I just say state equals Bowie, cost-based subtomain goes, oh, this is indexed and it's partitioned, and I can access the partition that contains the Bowies, and I'll use the index to do that. If I ever ran status equals to process, Oracle goes, oh, that's indexed. Unfortunately, processed, I can't access the index. It's unusable. There's nothing in there. I'm forced to either use a different index or do a full table scan. Now, a very common question is, well, what should be the correct size of an index? All right, and there's all sorts of strategies on this. One really easy strategy is to do the following. I'm just going to create a table here. I'm just basing it on DBA objects and whatever. I'm just going to say explain plan for create my index. And part of the note is the actual estimated size of this index. And guess what? This estimate is pretty accurate as long as you keep a couple golden rules. All right. Now, if I create my index, guess what? Yeah, it's absolutely in the right ballpark. It's about 150 meg. It's done this precisely. Now, I've got another column, which is subject object name, which has got lots of nulls. Now, this estimate is not so good. So I'm going to say, what's the size of this? Oracle says 67 meg, and in actual fact, it's about 2 meg. Why? When it does its estimate, Oracle assumes every index entry is populated. But if you've got lots of nulls, those nulls don't live inside the index. So Oracle can overestimate this. But to fix this, all you need to do is work out what is the ratio of data that is nulls, and use that same ratio here to get you back to your usual correct estimate. The other thing that's critical, you must have reasonably accurate statistics. So this is based on statistics. So Oracle can guesstimate the cost of the size of this. So what I'm doing here is I'm doubling the size of my table, but I'm not creating new stats. So the estimates is still the same old estimate. So I need accurate statistics as well. But if I've got accurate stats and I know the ratio of my nulls to not nulls, this is a really cheap, quick, easy way to estimate the actual size of my indexes. And finally, I've got a couple of minutes. Give me almost there. I've got 1 minute, but I'll do this very quickly. Multiple indexes. I can create multiple indexes on the same column list from 12.1. And there's a couple key reasons why I want to do this. So as an example, I'm going to create a very simple table on Bowie, very simple partition table. All right. So I've just got a couple indexes on ID. And just note, I've created a non-unique index. And because you've attended my seminar and I've told you, actually, you really should use unique indexes, don't use non-unique. Bugger. All right, I'm going to create this now to be a unique index. So I try to create a unique index, and of course it says you can't because you already got an index on the ID. Well, let's make it invisible. It doesn't matter. Previous to 12.1, you can't create the same index on the same column list. Okay, then, well, let's drop the index. You can't drop the index because the index is necessary to enforce the primary key. So now, if I wanted to convert it, you have to go, well, I have to drop the primary key, so I can then drop the index. Now I don't have a primary key or an index. Now I've got this period of time where basically I have to have a downtime to do this. I can't possibly live with this table not having an index on the primary key. 12.2, I can do this. I can create the index as long as the second index is invisible. Only one index can be visible at the time. But the benefit now is in the hour and a half it takes for me to create this massive index, I can create both of them at the same time. Then what I can do something like this. I can modify my primary key to use my currently invisible index. Oracle doesn't care about that. It's a viable index. You can have an invisible index in that scenario. My downtime now effectively is this. The time it takes me to change something from being invisible to being visible. Because I want to make my new one, my old one invisible and my new one visible. So I've got this split period of time where I have two invisible indexes. But literally it's as quick as you can hit enter for this. That is now your downtime. Much better than the hour and a half they used to have before. So either you want to create an index which currently is unique, or maybe it's a local and you want to make it global, vice versa, or maybe you just got normal index, you want to convert them to be bitmap indexes, or you want it to be reverse key index to get rid of. There's all these scenarios where you've created one index in one way and now you wish you created a different way. And now you've got a strategy to do that because you're allowed to create the second index as invisible and then you flip and flop the statuses. Alrighty. Thank you very much. I think I'm just about on time, but like with Connor, I'm more than happy to sit around and answer any questions and whatever.